now I'm going to try and measure the peak force of throwing this ball, how high I can throw it, and I've got a reference object that I can use to standardize the length of the distance in the frame that I'm going to use to throw this ball. So I'm actually going to go a bit further because I want to be far away from the camera to try and get a better measure of how high I can throw. It's a little less windy today, so hopefully there's a little bit less wind noise, and we can get a good recording out of this. Shoot a shot. So another note is when I set this up, I tried to line it up so the camera was facing this light post, so I had a pretty good idea of where I'd be in the center of the frame. I'm not sure quite how high I threw that ball, just looking at it, but I did 3 runs just to try and make sure I have a good frame that I can record. Also gives me some idea of how much variance I'm getting when I throw that ball. So when you set your recordings up, try and shoot for multiple tries of each condition.
Alright, so now we've got the data from the 3 throws we just looked at put into Excel. We have a separate video later on in this module that will show you how to calculate all the things you're seeing here. But for now we want to just look at what the impact of this is and some of the math and what we have going on inside this spreadsheet. So again, we have the length of the paddle, which I held up in the video to normalize the distances here so we can convert all of the coordinates from pixels into meters. And we have the time here in milliseconds, and we convert that into seconds just by dividing by 1000. And then I've also filtered this data because I noticed there was quite a bit of noise inside the video in this longer throw, partly because we're further away from the camera, so our resolution of each pixel has gotten worse. But there was also some temporal things that were going weird, where the distance between each frame was not constant, and so we had some frames that were longer than others. I don't know if that's a function of the compression of the camera that I was using, basically my cell phone, or something else. The goal here inside this activity, or at least I was trying to achieve, was trying to figure out what the maximum height of the throw that I could achieve was. And again, did the 3 throws as well as the maximum force when I was throwing the ball or when I was kind of crouching down and throwing it upwards. I was also interested in trying to find the drag on the ball, or show the force of drag on the ball when it was going through the arc. However, that last one sort of ended up being a bit problematic, and we'll talk about that in a second. So the first one here, the maximum height, is probably the easiest thing. So I have the position, which is just converted horizontal coordinate in pixels into meters. And then I take the maximum of that entire row. So again, this whole row here is the position, the X is the height, and the Y is the width, because my videos are kind of rotated a little bit there. And so I can do that, and again I did that for all 3 throws. I also made a series of plots just to make it a little bit easier to see these. And so you can see I have the 3 throws here, 1, 2, 3, and I've also got the time series, so you can see kind of there's the squat down, the release, and then a parabolic arc as the ball travels through the air. And you can see the maximum kind of around here in this 6 to 7 meter range. So there's the actual values on that. On the maximum force, this is a little bit more difficult to calculate. Again, we got to consider how much force is the weight of the ball applying to my hands, and then as well as the amount of force generated by the acceleration of the ball upwards. And you want to make sure that when you're doing these that you're doing them in the right direction. So if I think about a ball sitting on a table, right, if I'm just holding it flat or if it's not moving at all, then the table applies its weight of, or the weight of the ball, right, to the ball to keep it still, and the ball applies its weight to the table because again, it has its inertia, right? So if I'm going to throw the ball upwards, I want to make sure that the weight of the ball, right, is being added to times the acceleration of the ball in the vertical direction, because again, I need to accelerate that ball upwards. So if I want to accelerate that ball upwards, I have to apply a force to it in the vertical direction, which is opposite of gravity. So this is going to kind of add on to the weight. So what I'm doing here is I'm just taking the acceleration of the ball due to gravity, the acceleration that I calculated in the coordinate frames, right? And then I'll multiply that times the mass of the ball in kilograms to get the maximum force newtons. And really I'm getting the force that is being applied to the ball through the entire arc, and then the maximum is just kind of occurs at that first when I'm throwing the ball up. There probably is also a higher force when the ball hits the ground and kind of inverts, but I don't have that in my recording, so I don't have to worry about that throwing my max off. You can see this up here. And I should also see that this force on the ball, um, actually I'm not calculating out the entire force, I calculate it over here actually later, is close to zero. It's the same equation when the ball's in free fall, right? So when the ball's in free fall, the force on it is very small. However, when I've calculated the frictional force, I tried plotting the frictional force versus the velocity of the ball, and this is actually velocity of the ball here on the horizontal axis and the frictional force on the z-axis. This data was very noisy, and so we didn't get a good approximation of what the frictional force was. There is kind of a trend here between the velocity and the friction, where there's a kind of a a downward force on the ball as it's going up and an upward force on the ball as it's going down. But was not super critical, and I think it partly is just because the frictional force inside this system is not very large, and it actually fits a parabolic arc pretty well. And I can actually show this inside this plot here. This is a fourth order polynomial, which would include some aspects of friction, and it fits the plot fairly well. But even if I move to a second order polynomial, which would not include friction, which you just said pure just acceleration due to gravity, we still have a very, very good fit. So there's just not a large frictional component to the travel of the ball inside this system, right? There's also some error here in the scaling factors, and so my acceleration due to gravity doesn't actually match what it should be, but it's not too far off. All right, one other thing here, if you notice, I also have the 3 separate sheets for each throw. One of the things that you want to do when setting these up is if you can set up all the math in one sheet, then you can really just copy and paste the entire sheet, and then all you have to do is change the input data and the ranges, and it'll automatically calculate the rest of the stuff for you. So that's one of the niceties of Excel, is that if you have everything set up cleanly, you can just use that to kind of quickly calculate second, third, fourth, fifth, however many different trials of a task you want to do. And then again, on these plots, I just copied and pasted them into each other. So you can copy the plot and paste it into a new sheet, and do the same thing with the other plots and other sheets to combine them together. Another thing here that made the frictional force difficult to calculate is the noise inside this system. So I actually did some filtering inside this data set. In this case, I used the 3-point filter, or 3-point average filter, where I'm just taking the average of the previous, the current, and the next position. That smoothed things out a bit, but if I look at the raw data for the acceleration especially, it's very, very noisy. So this actually shows 3 different filters. There is the raw data, there is a 3-point filter, and then there's another 5-point filter after that. And there's a big difference in how this behaves, and you can see that especially in the free fall, where you expect the acceleration due to gravity to be fairly constant, not until I get to that higher, more aggressive filter do I see a fairly flat line there. So this data is pretty noisy, and so getting that approximation of those higher order derivatives gets a little bit sketchy. All right, so hopefully that's interesting to you guys, and the next part of this task, you guys will go through and follow along with an additional set of videos that shows how these are made and try and apply them to an activity of your choosing.